Please confirm that you can see the presentation. Hello?
Yes, sir.
Okay, thank you. So let me just briefly recall a few things. In the last class, we went up to, we completed the discussion of derivatives, derivatives involving the vector differential operator del. Both the first and the second order derivatives we finished discussing, and please check, I have also uploaded all the notes up to page number 35. This is the point where we finished the discussion on derivatives. Thereafter, we began the discussion on line element, surface element, and volume element. This is preparatory to our taking up discussions on vector integration. We have talked about vector differentiation so far, divergence, gradient, curl, and now we shall take up vector integration. So in order to do so, we had to understand some basic ideas about line element, surface element, and the volume element. So in the Cartesian, I'm just briefly revising a few points taken up in the last class. So in the Cartesian coordinate system, what is the line element, dl? Basically, in the Cartesian coordinate system, you have to traverse 3 steps in the 3 coordinates. In the x coordinate, the step that you traverse is dx x cap. In the y coordinate, the step that you traverse is dy y cap. And in the z coordinate, the step that you traverse is dz z cap. And then you add all the 3 steps vectorially. This is the principle that shall apply in all the coordinate systems. You can see x cap, y cap, z cap along the 3 unit vector directions. What is the step traversed? And then the vector sum of all the 3 steps will give you the line element. And so once you have found the line element, as it happens, this line element defines an imaginary cuboid in 3-dimensional space described by the Cartesian coordinates x, y, z. Now the next task is for you to find the surface area element. And so there are 3 independent surfaces, although this cuboid has got 6 surfaces, 6 faces, but out of these 6, 3 are independent. And what are those 3? 1, 2, 2, 3, 3, 1, where 1, 2, and 3 stand for x, y, and z. So when you take the cross product of that, you don't even have to have anything understood geometrically. As soon as you have the line element, everything follows in a very state, precisely defined mathematical order. So even if you're algebraically speaking, that is, you don't have to worry about even the geometry if you can't. So 1 cross 2 will give you dx dy z cap, because x cap cross y cap is z cap. Similarly, next thing is 2 cross 3. I've written that in the margin. 2 cross 3 will be dy dz x cap, because y cap cross z cap gives x cap. Take a look at the notes that have been sent to you already. And then finally 3 cross 1, z and x, dz dx y cap, y cap, because z cap cross x cap is y cap. So those are the 3 surface area elements, and the direction will be perpendicular to the surface. But every surface has got 2 faces. Just look at a sheet of paper. It has got a top face and a bottom face. So which surface are you talking about? I mean, the direction will be normal to which surface, the top surface or the bottom surface? Well, you will have to define that. It will be normal to both the surfaces, but if it's a closed surface, then the outward direction will be considered positive. For instance, if you take a sphere, which is a closed surface, and so the radial vector will be normal at every point on the surface of the sphere. So as it stands over here, direction is normal to the surface, the direction of the radial vector. And since the sphere is a closed surface, the radial vector will be pointing outwards, because the radius always points away from the center to outwards, going all the way up to infinity, like that. So when you have a closed surface, the outward direction will be positive. Okay, so you have, I mean, this principle will apply in all the cases, 1 cross 2, 2 cross 3, 3 cross 1. Finding the surface element is slightly complicated. Finding the volume element is not. The volume element will always be the same. Let us see. Incidentally, be a little mindful about the symbols that are employed. Line element, L as in line, DL vector. Surface element, dA vector, A as in area, as in surface. So surface element, dA vector. And volume element, well, nobody is writing dV, it's written as d tau. So d tau. By the way, I have uploaded the book of David Griffiths' Electrodynamics. The book is in the DJView format because I mean, there's a PDF file, but the PDF file is very large in size. The DJView format has got a lightweight structure, the same book. I mean, I think the PDF file was 65 megabytes or something of that order, whereas this DJView format is 5 megabytes. So it has been uploaded in your classroom. Please check. And I hope you should be able to see it. I mean, those who use Linux will be able to see it automatically just by clicking on it. And those who use Windows may need a DJView to PDF converter, but that's freely available on the internet. Why am I referring to all these things? Because these symbols are all used in your book, David Griffiths, your textbook. That's the state textbook that you have to follow. So there I'm using the terminology from that book only. So here you have volume element d tau, tau as in the Greek letter tau, which is the equivalent of T in the English language. So d tau. Now here we shall again use the idea of the triple scalar product that we have referred to, A dot B cross C. So what we shall do is that B cross C, I mean, it's whatever combination you use, it doesn't really matter. Ultimately, it'll just, let's take one example, 1 cross 2 is like your B cross C. 1 cross 2 will give you dx dy z cap. And then you have to dot it with the third vector, which is dz z cap. So z cap dot z cap will be 1. And then you will just have dx dy dz. So you can see that from what I've written in the margin, here I've taken x, y, and z outside. So then I can also take dy cross dz will give you in dot dx x cap. So this will again give you dx dy dz. And similarly for the third thing, z and x first crossed with each other, and then the outcome is dotted with y. Again, the result will be the same, dx dy dz. So the volume element is a scalar. That's the first thing to note. So that makes your task so much easier. You don't have to worry about vector direction. But most importantly, whatever combination you take, the volume element is just the same. The volume element is the easiest thing to find. As soon as you have the line element, it will just be the magnitude of the step size in the first vector into the magnitude of the step size of the second vector into the magnitude of the step size of the third vector, dx dy dz. When I say into, I'm not referring to any dot or cross product because we are not considering the outcome is not a vector. So you can just take the magnitude. So any other coordinate system, you just look for d whatever, and d whatever over here, and then multiply all the three d's to get something like this, dx, dy, dz in this case. So just to round up the full discussion, volume element is a scalar. It has got only a single value regardless of whatever combination or permutation you try, permutation actually, of x, y, z's you try, the final outcome will be the same. So that's the simplest thing that you have. Line element is this. Step taken in the first unit vector, steps taken in the first coordinate, step taken in the second coordinate, and step taken in the third coordinate. All of the three added up vectorially as the line element. Surface element is a little difficult. There you shall have to apply your knowledge of the cross product of vectors. So with these three things, we shall now begin our discussion of vector integrals. First, a line integral. You have the line integral of a vector defined like this. Remember, line element is a vector. So if you have to take the integral of another vector, line integral of another vector, you have to be a little careful. Don't just put the two vectors next to each other. Two vectors as in the given vector A over here and the line element vector dl here. You have to be a little careful. You have to put a dot. That is the A and B are the limits of the integration. Line element is after all displacement. This dl is displacement. You started from this vertex on the bottom of the back face, left bottom back face, to this vertex on the right top front face. So basically from here to here through the depth diagonal you have traveled. That is the line element. But what is the line element to be seen as? It's after all a displacement. dl is a displacement. If it is a displacement, and what is displacement understood to be? Displacement is understood to be the difference between the position of two vectors A and B. Position is a vector. I hope you recognize that fact. And change of position is known as displacement. So what is happening over here is that you're going from position A to position B. Both are vectors. And so that's why the position, these vector arrows are put. Okay. Now, if you have a closed loop, a different symbol is to be used, meaning you start from A, you go to B, and you come back to A once again. That is to say, I mean, you just go around in a cycle. If that is so, I mean, I've written A is equal to B, meaning you just start from A and then you go to A again. Well, but you don't write two A's at both ends. What you write is a closed loop integral. If you have a closed loop integral, then the symbol of a closed loop integral is this, integration with a closed circle over that. Next is surface integral. What about a surface integral? In the case of a surface integral, it is, remember once again, surface element is also a vector, dA. And if it is a vector, then again you have to be careful. How do you put it next to another vector? It's capital A dot d small a. So put next to each other. S subscript implies a surface integration, integral over a surface. And so when you have a closed surface, again, closed surface as in a football, let's say. Incidentally, what does a closed loop in the previous example, example number discussion look like? Take a string. You hold the two ends of the string apart, that is an open line. You take the two ends of the string together and glue them up, let's say. So you will now have a closed loop. The string has become a closed loop. A closed loop looks like that. Similarly, a surface. What does a closed surface look like? Imagine a sheet of paper. A sheet of paper is an open surface. It has got edges, just like an open string has got two end points. Similarly, an open sheet or an open surface has got bounding perimeters, edges. A sheet of paper has got four sharp edges, the two length edges and the two breadth edges. So it's a sheet of paper. But what does a closed surface look like? A closed surface is like the surface of a football. A football doesn't have any open edge. Everywhere on the surface of a football, you run your hand, you will not find any open edge. It's a closed surface. So that's a closed surface integral. What about a volume integral? Volume element d tau is a scalar. So here you can be a little casual. D tau. So you can, I mean, you don't have to worry about how you should put it next to either a scalar or a vector. If it is a vector scalar quantity, it is simply just rho, as in a scalar quantity d tau. This subscript v below the integral implies volume integration. This subscript s below the integral implies surface integration. In the case of line integral, I have not put anything because that's the most standard integral you can get. But certain books, and occasionally I myself will also follow that terminology, will put a P here. P as in point to point or perimeter, maybe, I don't know, I mean, how you call it. Some authors put a P down there. But S subscript here is a surface, and V subscript here is a volume. Incidentally, some books, instead of putting S, will put two integral signs. because you have to, if you put two integral signs, it means dA, two d's, one integral over dx, one integral over dy, like that. And likewise, if you have a volume integral, you'll put three integral signs, one after the next to the other, like that. Why? Because there are three d's in a volume integral. So for every d, there will be an integral sign. So there are different terminologies used, but I'm not getting into that too many of those discussions. When you have an S subscript written over here, it means it's a surface integral. And if it's a surface integral, then be it understood that you have to perform two integrations. Similarly, you can put a V over here. You have a V, it means that you'll have to perform three integrations because d tau has got three d's, dx, dy, dz in this case. And similarly, when you are integrating over a volume, a d tau, volume vector integral a d tau for a vector. So that is the volume integral. Okay, now let us see. We'll have to look at certain theorems of vectors. So with the understanding of vector integrals, we shall look at some basic theorems of involving vector integration. First is the theorem of gradients. In one dimension, f is given as a function of x. Okay, fine. So if you're going from point A to point B, finding the value of f over the full range, you take a small element df and then you integrate. Next thing that you do is, instead of taking an integration over df, what you do is you write df dx into dx. I hope you have no challenge in understanding what has been done over here, just a bit of a chain rule something. These dx and these dx actually are supposed to cancel out. So you can write this df integral as this df dx into dx. Okay, that's one way. And the other way is that when you integrate df, you ultimately get f. Integral d of something is that something. Standard rule of integral calculus. So so this d and this integral sign will cancel, and you're just left with f b minus fa. Integration of this is f, and then you take the difference between the two limiting values, fb minus fa. So from here you can get here, and from here you can get here. So these two things are equivalent. A goes to C and A goes to B, therefore B must also go to C. If that is so, now what we will do, by the same principle, we apply it in 3-dimension. In 3-dimension, instead of f depending on x, we have a function phi depending on all the three spatial coordinates x, y, z. So d phi, going from position A to position B. Note the vectors over there. What can we do with d phi? We have already discussed this thing, gradient of phi dot dl. This can be written. I mean, just like we have written df is equal to df dx into dx, d phi I'm writing as the gradient of phi dot dl. Okay. And then this integral d phi will be just phi with the difference between position phi value at B and phi value at A. So you have to take the difference between these two. So this goes to this. This also goes to this. Therefore, this must be equal to this. This is known as the theorem of gradients. Gradient of phi dot dl, line integral of the gradient of phi, is simply the difference of phi between the two limits A and B, which are position vectors, phi of B minus phi of A. So first thing, let's look at the outcome. Phi depends only on the positions. You can see we don't have to worry about how we are going from A to B. Just the final values are most important. Whether we are going through any intermediate value doesn't matter. So it will depend on the positions. Okay, that's number one, phi B minus phi A. When A is equal to B, meaning you are going over a full loop integral. A is equal to B. You're going over a full closed loop. If you're going over a full closed loop, if A is equal to B, then gradient of phi dot dl, this thing will be phi A minus phi A. Closed loop integral, that is what. I've just made a slight error over here. I've not written this arrow sign. So this vector arrow is not there. So you can see, just make a note of that correction to be made. So the vector arrow he should be here. So gradient of I dot dl closed loop integral will give you 0. And note also something, that if you are working with a conservative force, then a conservative force can be written as the negative gradient of a potential function. If it is written as the negative gradient of a potential function, work done over a closed loop of a conservative force field is equal to 0. Just replace gradient of phi with minus f. Minus sign goes to this side. Minus f dot dl closed loop integral is equal to 0. So the minus sign really doesn't matter. So basically it means f dot dl closed loop integral is equal to 0 in a conservative force. Now do you see how we talk about work done in a gravitational field over a closed cycle is 0? I ask you to lift a heavy suitcase upstairs. You go upstairs, and then I ask you to bring the suitcase down again from upstairs to downstairs. You thought that you had done a good deal of labor, but the fact is that in a conservative field, you will have to accept that the work that you have done ultimately is equal to 0, although you have lifted a heavy weight up and down, carried a heavy weight up and down from the ground floor, let's say, to the roof of your house, and then come down again. So that is what it is. I will begin a new set of notes now. Later, I will send you all these things. I'll begin a new set of notes to continue this discussion. So please just bear with me as I switch over to the new set of slides. I'll stop the sharing of this. So that is the gradient theorem. Now we shall just like you can do an integration of with the help of the gradient of a vector, you can also apply the divergence theorem. But before I get into the details, you please confirm from your side that you are able to see this presentation. Please confirm, one of you. Hello?
Yes, sir.
Okay, thank you. So there we are. First, we'll look at these things with an overview soon enough, but first let us now try to understand the divergence theorem. Like you have the gradient of phi dot dl going from position A to position B gives you phi b minus phi a. Similarly, when you talk about divergence of A is a vector. You take the volume integral of that. Volume integral d tau with V written over here is equal to closed loop integral of A dot dA. Now, in the previous page, in the previous slide, I'm sorry, I did not stress on this one fact. I have talked about closed line integral and open line integral. You take a line integral, you go from position A to position B. And if you come back to position A again, you have a closed loop integration. Just now we discussed that thing. For instance, in a conservative field, a closed loop line integral will give you 0 outcome. In the case of a surface, once again, you have an open surface and a closed surface. I discussed an example. An open surface is a sheet of paper. And just as an example, a sheet of paper. A sheet of paper, how would you know an open surface geometrically from a closed surface? Very simple. An open surface is always bound by edges. A sheet of paper is bound by 4 edges, 2 length edges and 2 breadth edges. So that is an open surface. But a closed surface has no edge, no sharp edge. For instance, a football. A football is a closed surface. And so you will not find everywhere, you'll see there's no opening. So that's one thing. But in the case of volume, I made no such distinction. I did not say open volume or closed volume. Why? Because volume must be defined within a closed surface. If I say how much air is contained in this room, first you will have to close the doors and windows of your room to define a closed volume within which you are studying the amount of air trapped in your room. Suppose you are under a shed. with no walls on four sides. You just have a roof, a shed, and you have a ground to stand upon. The kind of shed that you have at bus stops, wherever. So, will it make much sense for me to say how much air is trapped within this shed? No. Why not? Because there are no bounding surfaces, no bounding walls. I need four bounding walls to define a closed surface here. The roof and the ground, and then the four walls, a front wall and a back wall, and a right wall and a left wall. Just as you can do so in your room. At this very moment, you are sitting in your room, I presume. So if you close all the doors and windows, then you'll define a closed surface, and thereafter it will make some meaning for you to say that this much air is contained in my room. So whenever we say
Sir,
hello,
sir, hello.
yes, yes,
So, what about open cylinder?
open cylinder doesn't trap any volume. There's
No,
nothing.
sir. And open cylinder has a surface.
Yes.
Then will it be an open surface or closed surface?
No, what do you mean by an open cylinder? An open cylinder, if the lid,
Open cylinder as in just the curved surface and not the two circles on top and bottom.
no, so then it's not. It's I mean, what can you hold anything inside that?
Yes.
So, so volume must always be defined within a closed surface. A football has a volume, right?
Yes. Yes.
But sheet of paper, which is an open surface, doesn't enclose any defined volume. So you can think of a sheet of paper like your cylinder. You roll up the sheet of paper, but it will still have an open top disk face and an open bottom disk face. But
Yes.
it will just have, so a volume is always defined within closed surfaces. That is why I did not make any distinction about an open volume or a closed volume. Volume, by definition, is so whoever's asked me the question or whoever else, please mute the mic now. Please mute the mic. Yes. So there's some noise coming. So cylinder, I'm sorry, a volume by the default arrangement in the case of a volume is closed within a closed surface. So here we get to this divergence theorem. In the divergence theorem, you have to carry out a volume integration, and the volume integration will take you to a closed surface integration on the right hand side. Just like in the case of the gradient theorem, a line integration took you to the values of the function at the two boundary points, phi b minus phi a. So here the volume is enclosed within a closed surface. So a volume integral will collapse onto a closed surface integral. I'll talk about this thing geometrically soon enough, A dot dA. So just note that the left-hand side is a scalar quantity because divergence is a scalar quantity. Divergence dA is a scalar quantity, d tau is a scalar. And there on the right-hand side, you have got A dot dA, A and dot area element dA. So everything has to be scalar on both sides. So A dot A, I mean, what do you do? I mean, A is a vector, dA is all, d small a is also a vector. You have to get a scalar combination out of it because the left-hand side is a scalar. So there's only one way you can get a scalar out of two vectors, take a dot product. So A dot dA. This is known as the Gauss divergence theorem. It's a very important theorem and we shall use it again and again. So the Gauss divergence theorem depends only on the closed surface of a, as I mentioned over here, closed volume, depends only on the closed surface. You see, closed surface integration. There are two integrals to be performed over here because dA is actually dx dy. It's got two d's in reality. So it depends only on the closed surface of a closed volume. Okay. And what is this thing, A dot dA? A dot dA is actually the flux. Let us try to understand that. So here is a small area element dA. Okay. And now through this area element, vector lines, this capital A are the vector lines. They are piercing outwards through this area element. Now, dA, direction of dA is outwards to the closed surface as I have mentioned to you. So this is a part of a area element, which is a part of a larger closed surface, because ultimately we shall be performing a closed surface integral. So this is the direction of dA is outwards to the closed surface. This I mentioned. For instance, on the surface of a sphere, the direction, outward direction, is along the radial path. So this, you have to take the dot product of these two vectors. Now, what is the dot product of these two vectors? Vector A, capital A, and vector D, small a. You have to take the dot product. Ultimately, what is this thing? A into dA. What have you got over here? You have gathered all the field lines of vector capital A over this small area element. And that actually is the definition of a flux. I shouldn't use the word definition, understanding of the flux. What is flux? Loosely speaking, it is total number of vector field lines crossing a given area. Right. So what you are doing, this A dot dA is, you're just summing up all the two vector field lines crossing this small area element dA. So that is the flux that you have got. And of course, flux, I mean, this will just be, what is the definition of a dot product? Magnitude of vector A times magnitude of vector dA times cosine of the angle trapped between the two vectors. A, in this case, vector, angle alpha. So that is what the flux is. So basically, what you have got over here in the divergence theorem, Gauss divergence theorem on the right hand side, you have gathering the total flux enclosed, total flux passing through the enclosing closed surface. We will discuss these things. There's an interesting pattern for you to observe, but I'll touch upon that point later. I'll now go to the third vector theorem. See, there are three vector ways in which you can apply the vector differential operator. One way to apply it on a scalar, gradient of phi. Then with a vector, there are two ways to apply. What are the two ways? One is the divergence way and the other is the curl way. We have just finished discussing the divergence way. Now we shall have to worry about the curl way. So let us see. Theorem of curl. Curl of A dot dA. Curl of A dot dA. So basically you can see now what have we got over here. It's an open surface. See, I did not put a circle over here. Right. Open surface, curl of a vector, you're finding the flux of the curl of a vector through that open surface. Like, let's say, the sheet of paper. What is it now? But what bounds an open surface? An open surface is bound by a perimeter. I hope you realize that fact. Look at a sheet of paper in front of you right now. There are four bounding lines, two length lines and two breadth lines. Together, you define a perimeter. Unless you have a perimeter, you will not be able to define a surface. Just a while ago, I told you, define a surface within finite limits. I'm sorry. Just a while ago, I said that a volume is by default enclosed within a closed surface, as in the case of a football, right? A volume, or in the case of, let's say, a can. A tin can is like a cylinder. It has got a round barrel face and then a top lid and a bottom lid, a bottle, let's say, a jar, whatever it is. So they're all, the volume enclosed is the very statement that I'm, the statement itself, volume enclosed, means that I'm talking about a closed surface within which the volume is enclosed. You can't have enclosing unless closing meaning a surface, enclosed meaning as enclosed, closed within. So you have to have a bounding surface. Similarly, a sheet of paper. A sheet of paper is enclosed within a boundary perimeter. If you buy a plot of land, you can't just say, this is my land. Somebody will say, where? I mean, where does it end? Where does it begin? You will have to put a rectangular fencing, on a rectangular plot of land, you'll have to put a fencing. So that fence defines your perimeter. You own that part of land. So that perimeter is the boundary of an open surface. Otherwise, it will go all the way up to infinity. So here it is, so that when you carry out a surface integral, that surface integral will collapse on the surface integral of the curl of a vector, that integral will collapse on the boundary of the perimeter. So this P, as I have written over here, but I'll not do it all the time, P as in perimeter, S as in surface, and here V as in volume, S as in surface once again. You notice already something. The left-hand side is an integral over two spatial dimension, and the right-hand side is an integral over one spatial dimension. Here, the left-hand side is an integral over three spatial dimension, volume integral, and the right-hand side is an integral over two spatial dimensions. So the left-hand side is an integral that is one spatial dimension higher than the right-hand side. So I hope you're recognizing the pattern, which I shall discuss in detail shortly. But if you're astute enough, you should be able to realize this thing. Similarly, for the gradient integral, the left-hand side is an integral over the line, and the right-hand side collapses on the point. So the left-hand side point has got 0 dimension, line has got 1 dimension. Okay, so this, anyway, but to come to this story, the theorem of curl, this is known as the Stokes theorem. Right, Stokes's curl theorem. Just a minute. Sorry, just a minute. Yes. Now, here, let us see. Here is the open surface. I've drawn this circle over here. I could have drawn a sheet of paper, but a circle, a disc. Let's say just a card or something, a frisbee or whatever is like an open surface. This is a surface disc, right? The top surface of a tin cover of a can or something like that. It's got a small area element dA over here, whose direction is pointing upward. And so if you have a vector capital A on this surface, you take the curl of A, carry out a surface integral, and the value of that surface integral, of that open surface integral, will collapse on the boundary perimeter, which is this circular circumference of the disk. Okay, so what does the Stokes theorem imply? First thing, depends only on the boundary perimeter. I will come to the direction of dA shortly. Depends only on the boundary perimeter. The topography of the surface is immaterial. What do I mean by that? Just recall our discussion of the theorem of gradients. I said that in the theorem of gradients, gradient of phi dot dl collapses onto, going from position A to position B, collapses onto the value of phi b and phi a. How you go from position A to position B does not matter. And that is actually what happens when you do work done in a conservative field. I ask you to lift a suitcase, heavy suitcase, from the ground floor of our main CEP academic building, which I'm sorry to note that you haven't seen yet, because you haven't come to the campus yet. So our academic building has got many staircases, 3 or 4 staircases. So you can lift the suitcase up along any staircase. You can even lift it up along the outside drain pipe by scaling the wall, whatever you do. But if you're going from the ground floor to the top of the second floor, the roof, whatever staircase you take, it will not matter. The work done that you would have done will be, the work that you would have done will be the same. So regardless of the path you take, your line integral of the conservative field will not change. And similarly here also, regardless of the topography of the surface, because ultimately the integral is collapsing on the perimeter. As long as the perimeter is intact, the shape of the surface doesn't matter. Let me give you an example. You have bought a plot of land, right? Let's say a large plot of land. As long as you have the outer boundary fixed, you can dig a pit inside the land. You can dig a pit so there will be a bit of a valley in the surface. Let's say earlier it was a flat land, completely flat, just like a sheet of paper on your tabletop. There are 4 boundary edges. So if you've bought a rectangular plot of land, you want to do something, build a house or whatever it is. And so you dig a pit. So now your land will have a bit of a small valley, and then all the earth that you have dug out, you pile it up somewhere else within your own plot. So now you have a little hill. So you dig a pit, you raise a hill, whatever it is, but when you have to pay the corporation fees to the government, it doesn't matter whether your land goes up or down. It will only matter is how much area, flat area, let us say. I mean, the price that you will have to pay is the equivalent of how much flat area is confined within the perimeter. So it doesn't matter what is the shape of your land. As long as the perimeter is intact, it will be, you will not have to pay anything extra, or you will not be given any discount or whatever. And so it is that when you are carrying out this surface area integral, since the integral collapses only on the boundary perimeter, the surface can go, I mean, here within the disk, you can have a hill, you can have a trough, whatever. The topography, meaning what's the shape of the surface, the topography of the surface is immaterial. It doesn't matter. It depends only on the perimeter. Now the next point is that the integral vanishes for a closed surface. Why? Why does the integral vanish for a closed surface? Very important point. What is the property of a closed surface? A closed surface doesn't have a perimeter. A football doesn't have an edge. A perimeter is defined for an open surface. A perimeter defines the edge of the open surface, a sheet of paper, your plot of land around which you have put a fence. That's the perimeter. But a football is not defined by an open surface. A football is defined by a closed surface. And if there is it is defined by a closed surface, then this outer perimeter is not there. So dl, this integral will be meaningless. dl is 0. Right, the perimeter integral, the perimeter does not exist. So the integral will vanish. The right-hand side will become 0. So this integral will be equal to 0 over a closed surface. Why? I've just given you the answer. There is no perimeter. So, and then the last question is, what is the direction of dA? The direction of dA, this thing, you will say that, okay, I mean, if it's a closed surface, I'm fine. The direction will be outwards. But if it's an open surface, let us say it's a sheet of paper, what is the direction of dA on a sheet of paper? Because there is a top face of the sheet of paper and a bottom face, and the vector arrow is pointing up from the sheet of paper and going downwards also. So there are two faces, and each face has got a dA. So which dA should you take for your purposes? Here's the answer. Ultimately, you will have to, what is A dot dl? You take curl of A dot dA. And this right-hand side is A dot dl, meaning when you're doing A dot dl, you're gathering all the value of the vector dA on the perimeter and going around. dl is a small path that you travel along the circumference of this disk, right? Or, length or breadth, whatever. A little line element that you traverse along the perimeter. So you're gathering A dot dl, I'm sorry, gathering the value of A over this entire edge, the perimeter outside. Now, so suppose you're going in the, when you take dl, you are going in this case in the anti-clockwise direction. This is the anti-clockwise direction. If that is the anti-clockwise direction, then use your right hand. Look at your right hand, curl your fingers and stick your thumb upwards. So this will be the direction of the curling fingers, the direction of dl, vector dl, and this will be the dA is the direction of the thumb sticking upwards. So use your right hand to determine the direction of dl. dl can happen in two ways. dl can happen in an anti-clockwise direction, as in this case, or it can happen in a clockwise direction as you go in the other way. So if it is going in the clockwise direction, then you just have to turn your right hand downwards. You curl your fingers, point your thumb downwards as you do in thumbs down. You do thumbs up, curl your fingers in the anti-clockwise direction. The fingers will be tracing the direction of dl, and the sticking thumb will trace the point at the direction of dA. And if you are going in the other way, if you do thumbs down, then your fingers are curling in the clockwise direction and the thumb will be pointing downwards. So what is the direction of dA? That entirely depends on the way you want to travel along the perimeter. So if it is dl, then it will go upward. If dl, I'm sorry, if dl is anti-clockwise, dA will be going upwards. If dl is clockwise, dA will be going downwards. So that is the Stokes curl theorem. Now I shall come to an important point. This is what I wanted to touch upon. I'm calling this thing the geometrical layout. I'm not discussing any geometry as such. This geometrical layout is the way I have just defined. I've just discussed the way you collapse one set of one integral on another. Let us see. First, the theorem of gradient. The theorem of gradient says gradient of phi dot dl going from A to B. Sorry, just a minute. I hope the recording is on. Yeah. Gradient of phi dot dl going from A to B is equal to phi b minus phi a. Line integral of gradient of phi collapses on the value of the function phi at the two bounding points. What are the bounding points of a line? A line is a one-dimensional object, and the two bounding points of a line are the initial point and the final point. Take a string. There are 2 points. The string starts at one point and ends at the other point at the other end. So the first point is position vector A. The second point is position vector B. Gradient dot dl will give you the value of the function at the two the boundaries of a line, so to speak. What are the boundaries of a line? The two bounding points, B and A, position B and position A. So collapsing the line integral to two boundary points. Okay, so you notice line to point. What is a point? What is the dimension of a point? Point is zero dimensional. Line is one dimensional. So one dimension goes to zero dimension. Now let us look at the surface to line integral. The surface to line integral happens over the Stokes curl theorem. Curl of A dot dA, surface integral, will, what is a surface bounded by? A surface is bounded just as a line is bounded by 2 points. Similarly, a surface is bounded by its perimeter. So the surface integral of the curl of A vector will collapse at the value of the vector all around the perimeter. A dot dl, what is A dot dl? You have gathered the value of the vector A dot dl over the full loop, closed loop. You have gathered the value of the vector over the full closed loop. So summed up, integration is summation. You have summed up the value of the vector over the entire circumference, over the entire perimeter, P as in perimeter. Perimeter is a line. A perimeter is defined by a line, let's say your rectangular plot of area. So it's the total line, the two length and the two breadth. You have a circular area, it's the total circumference. So a perimeter is a line after all. So basically the Stokes curl vector theorem is the collapse of surface onto line. Line as in a one-dimensional geometry, surface as in a two-dimensional geometry. Now let us go to the Gauss divergence theorem. The Gauss divergence theorem collapses a volume integral on a surface integral. As you can see, a volume is always enclosed within a closed surface. Enclosed, meaning closed within. Enclosed in a closed surface. Enclosed by a closed surface. And so volume by default ends at the enclosing surface. So a volume integral of the divergence of A collapses the integral to the bounding surface of that volume, the full closed bounding surface of that volume, A dot dA. Volume will go to surface. Volume is three-dimensional, surface is two-dimensional. Okay, there are a few other things for you to note. Let us now go to all these things. First, zero dimension, one dimension. One dimension, two dimension. Two dimension, three dimension. Let us look at the left-hand side. The left-hand side is just a vector difference, just a differentiation into a corresponding element. That is how it looks like a differentiation into a corresponding element. So gradient of phi dot dl, just like we write df dx into dx. This is, after all, just like taking d phi. This thing is nothing but d phi. But what is d phi? D phi is just like df is equal to df dx into dx. And so it is. So you just have, instead of df, it's a differentiation times an element. A differentiation times an element. That pattern will always hold throughout. You see this thing? Curl is a differentiation. Gradient is a differentiation. Curl is a differentiation. Divergence is a differentiation. So this is basically differentiation times an element, and then the collapse is happening to a boundary which is one-dimensional lower on the right-hand side. Surface differentiation, surface integral is collapsing to line integral. Volume integral is collapsing to surface integral. Line integral is collapsing to the points. There are, I mean, a line just has got 2 points, nothing else, ends at 2 points. So if you have to sum everything, just go to the 2 points and sum them up. Okay. Now, the right-hand sides of all these integrals are scalars. You see, a dot dA is a scalar. A dot dl dot again is a scalar. Pi is a scalar function. So all the right-hand sides are scalars. If the right-hand sides are scalars, then the left-hand sides must also be scalars. Hence, you have before every element leads to a scalar. Dot dl, dot dA, and d tau is anyway a scalar by itself. So you don't have to worry about putting a dot across or whatever. And so, and in front of it, you have gradient, you have curl, and you have divergence. So that's the geometrical layout of this thing, or the way of, looking at it. So the fundamental principle is like this. Differentiation of a function multiplied by its corresponding element, volume here, surface here, line here. And what kind of differentiation? Not just any ordinary differentiation, divergence here, curl here, gradient here. But the principle is just that. Differentiation of a function times an element collapses that function to the bounding points. In this case, line, bounding points are the two boundaries are the two boundary points. Surface, in this case, the boundary is the perimeter. Volume, in this case, the boundary is the enclosing surface. So I have not done any deriving or anything of these three integral theorems. That's difficult, and that's also not really needed, because we are not going to do heavy-duty mathematics. We are going to use mathematics on a necessity basis to work out physics problems. That's the whole idea. So I've just discussed some salient points about these three integral theorems. Now we shall apply them in a physics context. Solenoidal and irrotational fields, forms of fields. So I have discussed so far that what is the definition of a solenoidal field. You'll straight away say divergence of that field will give you a scalar zero. What is the definition of an irrotational field? Curl of that field will be vector zero. Okay, fine, that is good. But then my question to you is not really a complete question. And this takes us back to an earlier discussion of ours. What is the equation of a line, straight line? From school level coordinate geometry, you will say that the equation of a straight line is y is equal to mx plus c. Yes, that is good, but then you should also have asked me, in what form do you want the equation of a straight line? Integral form or differential form? If it is the integral form, then y is equal to mx plus c is fine. But if it's in the differential form, you take the derivative of that. Dy dx is equal to m, which is a constant quantity. Or d2y dx squared is equal to 0, which is universally valid for any line that you draw. So as soon as I say what is the equation of a straight line, you'll immediately ask me, please be specific. In what form do you want the equation to be supplied? I'll say integral form. Your answer will be y is equal to mx plus c. And I'll say differential form. Your answer will be d2y dx squared is equal to 0, or dy dx is equal to constant. So the equation of a line can be expressed in either an integral form or a differential form. And similarly, solenoidal field and irrotational fields can also be expressed either in a differential form or an integral form. Here, you have a solenoidal field. Divergence of that solenoidal field is equal to 0. That is the differential form. Now let us apply the Gauss divergence theorem. When I apply the Gauss divergence theorem, it says that the volume integral of the divergence of a vector is equal to the closed surface integral of that vector. Now, if you have a solenoidal field, divergence of that vector is 0. If that is 0, the left-hand side will be 0 completely. Divergence is 0, nothing else to integrate, all that, gone, everything. So if that goes away, then on the right-hand side, you will have A dot dA. That will be equal to 0. But what is A dot dA? A dot dA is the flux of the vector A through the closed bounding surface. So the closed surface flux vanishes. So what is the signature of a solenoidal field? In the differential form, it is divergence of A is equal to 0. And in the integral form, as you can see, there's an integration over here. And I'm saying this to be the differential form because there's a divergence over here, which is a differential operator. And here you have an integral. So this is an integration that is being carried out. So you have an integral form. So the flux vanishes. So that will be the integral form. Where do you see this? In the case of magnetic fields, we shall discuss this thing later. I'm just talking about the math part of it now. In the case of magnetic fields, the closed surface integral vanishes. What about an irrotational field? The differential form of an irrotational field is that the curl of that field is equal to vector 0. Now let us apply this thing to the Stokes curl theorem. In the Stokes curl theorem, I have, by the way, I have omitted to put the S over here. Sorry, a surface integral S, but this is a perimeter integral, but you can understand it now by now. So the surface integral of curl of A, if curl of A is equal to 0, then the closed loop line integral will be equal to 0. Closed loop line integral is equal, so closed line integral vanishes, integral form. Example, work in a central field, electrostatic or gravitational field. What about gravitational field? Gravitational field is a central field. It depends only on the radial function r. If that is so, then curl of that central field will be equal to 0. And if curl of that central field is equal to 0, then the closed loop integral of that central field, let's say gravitational field is F, curl of F is equal to 0. And F dot dl over a closed loop is equal to 0. And what is F dot dl? F is force, dl is displacement. F dot dl is work. Work is force dot displacement. So work in a central field, whether it's electrostatic or gravitational. So closed line integral vanishes. So what is the signature of an irrotational field? Once again, you will ask me to be specific. If I want your answer in differential form, he will say curl of A is 0. In the integral form, as you can see, there's an integration sign over here. It'll be A dot dl is equal to 0. Okay, and now just a corollary of that. If you have a conservative field, A is minus gradient of psi. I'm now using a different terminology, not phi, I'm writing psi. So instead of E, I will write gradient of psi. I'm sorry, but we also know that the gradient of psi dot dl, line integral of the gradient of psi going from A to B is psi b minus psi a from the theorem of gradients. So if you have curl of A dot dA, and A is a conservative field, then I can substitute the A with minus gradient of psi. So minus gradient of psi over here, but curl of a gradient is 0. You know that. We have done this thing mathematically. Taken derivatives of vectors. The notes have been supplied to you. So if you have a conservative field, you can write A as the negative gradient of psi, but curl of a gradient is 0. So if curl of a gradient is 0, then minus gradient of psi, because this thing minus curl of gradient of psi will be A dot dl, curl of A dot dA will be A dot dl with the closed loop integral. A is written as minus gradient of psi. Minus gradient of psi dot dl will closed loop integral will be equal to 0. So since curl of the gradient is equal to 0, it means that the closed loop integral gradient of psi dot dl will be equal to 0, which is not a challenge really. It is consistent with the fact that when A is equal to B, this thing will be equal to 0. So that actually leads to, from this argument, you can straight away conclude that curl of the gradient of psi is equal to 0. So that is what I've tried to establish over here. I am writing this thing as gradient of psi dot dl as a closed loop line integral will be equal to 0. If closed loop line integral is equal to 0, then from there you can show this, or vice versa. By using curl of the gradient of psi is equal to 0, you can show that the closed loop line integral of the gradient of a function is equal to 0. So so that fairly well finishes our basic discussion on vector integrals. So we are in a position now to move on to talking about other kinds of coordinate systems. But before we do that, I'd like to discuss a few additional points involving the concepts of vector integrals. I shall supply you the notes later. So let me just stop the sharing of this page, and I shall, sorry, just a minute. Here, these are the additional notes. We have already discussed this thing. By the way, here is the equation of a straight line, integral form, differential form. I just discussed all that. There's an error here. It should be r squared. I'll correct this thing and I'll give you. So we have discussed all these things earlier. So I'll just quickly scroll down to where we have also discussed all this, right? I haven't supplied you the notes yet. I've sent you this first set of supplementary notes, but not this one. It will require some extra working. Conservative vector fields. I'd want to discuss this issue over here. Force fields. Now, if you remember, I talked about central forces and how equation of energy conservation, half mv squared plus E is, half mv squared plus potential function is equal to a constant E. Those are the things we discussed. And I said that it's a conservative field. Okay. Now you have a central force. F is equal to Fr r cap. Example is gravity or electrostatics. As you can see, this is the scalar functional part of R. And so is also this is a, and then you have the unit vector r cap here and here. So that's the definition of a central force. Here it is in the case of gravity, it is r squared, which was not there in the earlier thing. I'll correct it and I'll give you. So I derived the energy conservation equation from the for a one-dimensional case. But now, since we have done vector integral theorems, we can do it for 3D as well. Let us see. Curl of F is equal to 0 because the field is irrotational. And further, the curl of the gradient of a scalar function is also equal to 0. This is a general mathematical identity, vector 0. Now, if F is a force, we can write F is equal to mass into acceleration, m ddt of v. Now, what we are doing is that we are multiplying this equation with, we are dotting this equation, taking the dot product of this whole equation with v. So we are taking a dot v here and a dot v here, f dot v and m dv dt dot v. But what about v itself? V is displacement. V is equal to dl dt. dl is the displacement in time dt. Okay. So m v dot dv dt, this left hand side, it doesn't matter in what order you take dv dt dot v or v dot dv dt. So this thing doesn't matter. So that is equal to f dot v, but I'm taking the f dot v to the same side as this equation. So it is minus f dot v, where v is now something that I'm writing as dl dt is equal to 0. Okay. Now let us see this part, the first part. The first part is m V dot dV dt, that I can write as m by 2 ddt of V dot V. How so? Because V dot V is V squared. And if you have V dot V is V squared, you can see this thing will be, I mean, it is just this. If you take ddt of V dot V, what will you get? V dot dV dt plus V dot dV dt. So you will get 2 V dot dV dt. And that 2 and this 2 will cancel, and you'll get this thing. That's how we are writing it. Okay, so we have a dt here, ddt here, and a ddt here. So I'm writing this thing with a common differential operator. Ddt of m by 2 is a constant quantity, mass is constant. So m by 2 v dot v minus f dot dl. M by 2 v dot v minus f dot dl with a common operator. Ddt is equal to 0. And v dot v is v squared. If v dot v is v squared, so it will be half mv squared minus f dot dl is a constant in time. Is equal to 0, so this thing will be constant in time. So force is the proportional to the gradient of a scalar function, f dot dl. So force is proportional, so F is equal to beta gradient of phi, where beta is a constant quantity. Okay. So half mv squared minus beta gradient of phi dot dl is equal to constant. Now what I'm doing is that I'm putting two limits, a to r, for this part. A dot gradient of phi dot dl going from a to r. Now, when I'm taking this integral f dot dl, I'm putting see, in the first case the integration was over time, so this will be a constant in time, right? A constant in time. Now, in the second case, I'm carrying out an integration over space. Dl is a space element, line element in space, right? So this integration will be over the spatial position. A is a reference position, A to R. So gradient of phi dot dl A to R will be phi at R minus phi at A. So this you get by the gradient theorem. Okay. And what have you got? Gradient of phi dot R minus phi dot A is, very important point, is the potential difference at R with respect to a reference value phi A at position A. I hope you have learnt very well at school that we don't measure potential. We always measure potential difference with respect to a reference point. In all your, let us say, electricity problems, you'll say potential difference applied between this point and this point in a circuit is potential drop, potential difference. So that is the thing. You're not measuring potential, you're measuring potential difference. It comes from this gradient theorem actually. Okay, so half mv squared minus beta, this thing will be phi r minus phi a is equal to constant. Now we are writing beta equal to -1. That's what we discussed earlier. If I write beta equal to -1, then I'll get half mv squared minus into minus beta will be equal to 1. So half mv squared plus phi. And then there is this phi of A. Phi of A is a constant quantity. I'm taking it to the right-hand side. So now you see half mv squared plus phi of R is a constant earlier that we got in time, plus another constant, phi at A. Phi at A is the potential at a reference point A. That is also constant. So these two constants add up to a new constant that we defined as the total energy. Half mv squared plus phi R is equal to E. So this is the conservation of energy principle that you can do in all three spatial coordinates. dl, where dl is dxx cap plus dyy cap plus dzz cap. Earlier when we established the energy conservation principle, we did it for one dimension only, but now we can do it for 3 dimension. And that requires the understanding, but for that we have to await an understanding of the gradient theorem here. So that is how we do it. So that is the energy conservation principle. Now when beta is equal to -1, if, as I said, f is equal to beta gradient phi, so f will be minus gradient phi. So in a conservative system, fr is the negative gradient of a scalar function of potential. And since gradient of the, sorry, curl of the gradient of phi is equal to 0, then a curl of f will also be 0. Hence, a conservative field is also an irrotational field. We discussed this thing in one of the tutorials, I think the first tutorial, in which we discussed that as soon as you see the word conservative, be it understood that you are being asked to find, you have to apply the irrotational condition. So you have been told a certain vector A, let's say, is a conservative vector. So immediately you will write curl of A is equal to 0. So that is what. So conservative field is also irrotational. And why are we calling a conservative field of force? Because when the kinetic energy increases, the potential energy decreases, and vice versa. So that is what you have over here. Kinetic energy will increase, the potential energy will decrease, and the sum will be a constant. So one has to go up, the other has to go down. The sum of the two quantities is a conserved quantity, which is the total energy. There are just a few additional points on vector integrals that I will just quickly touch upon. Is the format of the integrals. The format of the integrals is that if you have f of x, then the integral fx dx is equal to going from a to b. The general format of all the integrals, if you notice, line integral, surface integral, all these two especially, you have the first limit and the second limit, function of a variable, x in this case, and d of that variable. So this format also holds in vector integrals. This is something important for you to understand. A, function of space, so therefore you will have to put dl, dA, whatever. Except that if it's a vector, you'll have to worry about dot cross, all that business. Then from the first limit to the second limit. As in the case of line integral, let's say. All right. So that's what you do. A dot dl. A is a function of space, so you have dl, and then from the first position to the second position you go. Okay, this is something that I touched upon. I'm just writing it down for your record. Is that boundaries in various dimension in one dimension. If the integral is over a line, then the limits are the two geometrical points at both ends of the line. Two dimension. If the integration is over an open surface, the limit of the integral is the boundary of the open surface, that is the perimeter. In three dimension, if the integration is over a volume, the limit of the integration is the surface bounding the volume. A volume is always defined within a bounding volume. Remember that particular point. Okay. Cyclic integral in the gradient theorem, like I mentioned to you, d phi, a to b, gradient of phi dot dl, d phi can be written as this, going from a to b is phi b minus phi a. When a is equal to b, this closed loop integral dot dl will be equal to 0. Closed surface in the curl theorem, I told you this thing will be equal to 0. Surface integral curl of a dot dA, this is the surface integral. A dot dl is the line integral. Now if the surface is closed, that is does not have a perimeter, then the integral is 0. If there is no perimeter, then there is no dl. Right, dl is the displacement along the perimeter, the boundary of the surface. But if you have a closed surface, such as the surface of the earth or the surface of a football, then the perimeter does not exist and dl doesn't stand over there, and so the right hand side will be 0. And then this is the point that I touched upon while discussing the main set of notes. The right hand side is a scalar. You just look at the geometrical layout, gradient of phi dl, phi b minus phi a going to b. This is the surface integral collapsing on the perimeter integral, the volume integral collapsing on the surface integral. Right. So the points that I mentioned over there, I'm setting it on record here. The right hand side is a scalar quantity in all the three cases. The left hand integral is one spatial higher dimension higher than the right integral. Area, volume, length, area, point, length. The right hand side here is not an integral, but what is an integral after all? The value of a function, what are these integrals after all? The value of the function gathered at the boundary points. In the case of the surface, it's the integral that will mean integrating along the perimeter. In the case of a volume, it will mean integrating along the surface, all over the surface. But in the case of line element, you don't have to worry about that because there are just two boundary points. So just the values of the two boundary points that you are doing. Right, so the left integrals have three vector derivatives. That's the important point. Gradient, curl, divergence, like that. All the three vector derivatives. So it is derivative of a function into an element is equal to one dimension, the collapse of the function at the boundary of that element. See that feature also holds here, right? df dx, and then it's the collapse of the function at the two limits. So that is how it goes. One last point, and I shall end here with just a quick discussion. Additional points on solenoidal and irrotational fields. If you have a solenoidal field, divergence of A is equal to 0. And so divergence of A d tau is A dot dA. And so the flux will vanish, right? No, I think I should stop here because this thing will require a long discussion. But this point is okay. So maybe I should stop here. We have anyway run out of time. It's 9:45 now by my computer clock. So in the next class, which is on Wednesday, I shall discuss these additional points, solenoidal and irrotational fields, and thereafter we shall move on to discussing curvilinear coordinates, new set of coordinates. So, but this will be an important discussion and it will take some time also. Anyway, I'm stopping the sharing now. If you have any other questions to ask me, you may do so. Otherwise, I'm anyway stopping the recording. Takes up a lot of space. Can you please confirm, some of you, that